Welcome students. Today our session is about electrochemistry. So, this is Niroshan, chemistry faculty in Spark Academy. Welcome to our Spark Academy. Let's enter into our topic. So, let us see. This is a one-shot video regarding electrochemistry. Let us see all the topics of electrochemistry here. In general introduction, in this we have redox reactions. Let us see what is meant by redox reaction. In this we have a direct type of redox reaction and indirect type of redox reaction. You can see on the screen. In direct type, we have oxidation and reduction both carried out in same container, which happens in the same container. Here oxidation and reduction occurs in two separate half cells, that is indirect redox reaction. These two types of redox reactions we can observe in our electrochemistry. Let us see what is meant by oxidation and what is meant by reduction clearly. Understand these definitions because all the chapters and all the reactions are interlinked with this oxidation and reduction only. So, when here you can see a table, when loss of hydrogen happens, it is oxidation. When gain of hydrogen happens, it is reduction. Similarly with oxygen, gain of oxygens is oxidation and loss of oxygens is reduction. And loss of electrons is oxidation and gain of electrons is reduction. Here when oxidation happens, this oxidation number increases. When reduction happens, this oxidation number decreases. If you remember this table, you can easily remember the definitions of oxidation and reduction. So what is meant by oxidizing agent and reducing agent? Which undergoes reduction, that is known as oxidizing agent. Which undergoes oxidation, that is known as reducing agent. The agent which helps in gain of electrons, that is also known as oxidizing agent, and which donates electrons, that is reducing agent. And when oxidation number of its atoms increases, that is known as oxidizing agent. When oxidation number of its atoms decreases, that is known as reducing agent. So in this electrochemistry, we can see how a chemical energy, and electrical energy are related with each other. So they are interconnected. It is divided into two types of cells, galvanic cell and electrolytic cell. We can see these descriptions in the next slides. So this is the entire electrochemistry topic which we need to cover in our class 12. So what happens mainly in electrochemistry? It is mainly divided into two cells. First, it is galvanic cell or voltaic cell. It is divided into galvanic cell or voltaic cell, in which a chemical energy is converted into electrical energy here. In electrolytic cell, what happens? Electrical energy is converted into chemical energy. So that is the main part in our chapter. And we can see here spontaneous type of reactions and non-spontaneous type of reactions, which includes Gibbs free energy, that we can see here. Let us see the main difference between electrolytic cell and voltaic cell, that is galvanic cell. When electrical energy is transformed into chemical energy, that is electrolytic cell. When chemical energy is transformed into electrical energy, that is galvanic cell. You can see the difference here clearly. Just understand what is meant by galvanic cell and what is meant by electrolytic cell and what type of reactions will occur in these two types of cells. So when in electrolytic cell, that is where chemical energy is transformed into electrical energy, what happens here is the anode which we are taking is the positive electrode and the cathode which we are taking here is the negative electrode. This is opposite to the galvanic cell. What happens in galvanic cell? Anode will be a negative electrode and cathode is a positive electrode. In electrolytic cell, ions are discharged both at anode and cathode. In galvanic cell, ions are discharged only on the cathode. And next, if the electrodes are non-reactive or inert, concentration of the electrolyte decreases when the electric current is circulated due to electrolysis. It means if the electrodes are non-reactive, it means they do not participate in the reaction. What happens? The concentration of the electrolyte, which the solution which we are taking in the cell, decreases. The concentration decreases when the electricity is passed through it. What happens in galvanic cell? Concentration of the on the side of the anodic half cell increases while that of the cathodic cell decreases. As you can see, ions are discharged at cathode. Ions will be discharged at cathode. So anodic half cell concentration will be increased and that of cathodic half cell will be decreased when those two are connected by a wire. See, you can clearly see when we study in deep about these cells. And next, both the electrodes can be fitted in the same cell. So in only a single container we can fit both the electrodes here. The electrodes will be fitted in different cells. It means two different containers are taken and two electrodes are fitted in those two different containers. So this is galvanic cell or voltaic cell. As we have seen the differences regarding both these cells. See, in galvanic cell we are taking two different containers. Both are joined by a voltmeter. Both these electrodes are connected by a voltmeter, and to balance these concentrations we have used a salt bridge. Here in galvanic cell, the cathode is copper, which is the positive electrode, and here the cathode is zinc. It is a printing mistake here, and here the anode will be copper. This is anodic cell. A small mistake in this diagram. So just understand, this part, the left side part is the anodic cell and the right side part is the cathodic cell. Here when electricity is passed with the help of this voltmeter, what happens here is there will be transfer of electrons. How this transfer of electrons takes place, we can see here. This voltaic or galvanic cell consists of two half cells. So these are the two half cells in which where one part undergoes oxidation and one part undergoes reduction. See, the reactions occurring in the half cells are called half cell reactions, and the half cell in which oxidation takes place is called oxidation half cell, and the reaction in which reduction takes place, that is called reduction half cell. And next, the electrode where oxidation occurs is called anode, where oxidation occurs. So what is meant by oxidation? You can see loss of electrons. Where loss of electrons takes place, there oxidation happens, and that occurs at anode. And electron where reduction occurs is termed as cathode. So opposite to this, where gaining of electrons takes place, that is where reduction happens, that is cathode. And here electrons flow from cathode to anode. See, electrons flow from cathode to anode in the external circuit, through external circuit, and chemical energy is converted into electrical energy. This is the main point of the galvanic cell. So the net reaction of these two half cells, you can see here. Here we have in one of the container zinc sulfate solution and in one of the container copper sulfate solutions, right? Yeah. What happens when electricity is passed? This zinc loses two of its electrons and it is converted into Zn+2. And when reduction happens, that is in this solution, copper sulfate solution, when electricity is passed, reduction occurs. What happens? This reduction, that copper sulfate solution takes 2 electrons and it is converting into a copper. So what will be the net reaction? If you add both of these reactions, zinc plus copper plus 2 ions will give rise to zinc ions, which is in aqueous state, and copper is converted into a solid form. Here this reaction occurs. Zinc will loses two of its electrons and those 2 electrons will be gained by this copper ions, which is present in this CuSO4, and they are converted into pure copper. So this is the reaction. This is the net reaction happening in galvanic cell. So here to balance these 2 electrons, we are using these 2 solutions, we are using a salt bridge. So this is also important point. You need to learn what is the importance of the salt bridge. See, the following are the functions of the salt bridge. It helps to complete the connection of both half cells. See, if you see in this diagram, these both half cells will not be connected actually. So with the help of this salt bridge, both the solutions will be connected, and it prevents diffusion of the solutions in both the half cells. It prevents diffusion. It means it is helping not to mix both the zinc sulfate and copper sulfate solutions. It helps to build electrical neutrality. It means it is used to balance the electrons present in both the solutions. It avoids liquid-liquid junction potential. It means the potential difference arising when 2 liquids are in contact to each other. That will be avoided by this salt bridge. Next, here you also need to learn how to write a cell reaction. How to represent a cell reaction. So for this galvanic cell, what happens? During oxidation, zinc is converting into Zn+2 and this Cu+2 takes 2 electrons and is converting into Cu. See, here we need to represent the reaction happening in this galvanic cell in a single step, that is the IUPAC cell notation. Here first we need to represent the oxidation reaction. So what happens here? Zinc is converting into Zn+2. This is the oxidation, and next we are representing 2 lines which denotes the salt bridge. So after this salt bridge, you need to represent the reduction reaction. In reduction, what is happening here? The Cu+2 ions is converting into Cu. In brackets, next to this reactions, you need to mention the concentrations. So this is the complete representation of the cell. So what are the tricks to write cell notation? It is completely divided into 3 parts. First, you need to write the oxidation side of the reaction. Next, mention the salt bridge, and next write the reduction side. So in this way you need to represent a cell reaction. Next type of cell, which is electrolytic cell. So what happens in this cell? We are taking NaCl solution, as we have seen mainly in the differences. In this electrolytic cell, what happens? These 2 electrodes are taken in a single container. So you can see in the diagram here on this slide, These two electrodes are taken in a single container and they are connected to a battery where energy is supplied to this electrodes. What happens here? You can see reaction at cathode. Here what reaction happens? This Na plus will take electron and it is converting into Na. See here this Na plus, it is converting into Na, and what happens at cathode? We are taking here the molten NaCl solution. We have Na and Cl ions in this. Here the two Cl minus ions, here we have Cl minus ions, they are in ionic form. These will be converted into chlorine gas and by releasing 2 electrons. This chlorine ions will be converted into chlorine gas by releasing 2 electrons. So this is the cell reaction happening in this electrolytic cell. What happens? 2 NaCl, 2 moles of NaCl is converting into 2 moles of Na and Cl2. So this is the reaction which we can see in electrolytic cell. You can see the difference between the galvanic cell and the electrolytic cell clearly. There we have 2 containers, here we have a single container, and we can see they both are connected by a salt bridge. Here there is no salt bridge used, and same we have reactions at anode and reactions at cathode, and there is a cell reaction. In this way we can observe reactions in electrolytic cell. Next, what is meant by oxidation potential and reduction potential? So let us see what is meant by potential mainly. Potential. So if you define the term potential, it means when a solution is converting it into its ions, there will be a resulting potential developed in between it. It means, for example, we are taking NaCl. If it is converting into Na plus and Cl minus, a pure form is converting into its ionic form, what happens? There is a small type of energy produced. That energy is defined here as potential. So there are 2 types of potentials, oxidation potential and reduction potential. Here the tendency to lose electrons in the above case, that is we can see in this electrolytic cell. See here Na plus, the Na plus which loses its electrons, and it is converting into pure form of Na. So in the above case, here Na is losing its electrons, that is a oxidation is happening in that place. So that is known as oxidation potential. See, oxidation potential of half cells is inversely proportional to the concentration of ions in the solution. See, if NaCl is converting into Na, what happens to the concentration of NaCl? It gradually decreases. That is what explained here. It is, if oxidation potential increases, it decreases the concentration of the solution. Next, reduction potential. So what is meant by reduction potential? The tendency to gain the electrons. What happens to the chlorine here? It is gaining electrons, it is converting into chlorine gas. So what happens here? Reduction happens. Since reduction happens, the potential developed here is known as reduction potential. So according to IUPAC convention, the reduction potential alone can be called as the electrode potential. this reduction potential, it can be alone. It can be simply known as the electrode potential by with this notation. What happens? E naught of reduction, the potential is denoted by E naught. So when it is reduction, it is E naught of reduction. When it is oxidation, E naught of oxidation. Both are equal, but they have opposite in sign. These both are related in this way. E naught of reduction is equal to minus of E naught of oxidation. So that's why this reduction potential alone can be represented as electrode potential when it is E naught of reduction is equal to minus of E naught of oxidation. And next, let us see standard electrode potential. So when the conditions we apply here are in this way, that is, the potential difference developed between metal electrode and solution of ions. See, when a metal electrode and a solution are taken and when the conditions are of unit molarity 1 molar and at 1 atmospheric pressure and at 25 degrees centigrade, that potential developed at these conditions between the metal electrode and the solution, that is known as standard electrode potential. You can see this is also known as standard hydrogen electrode potential. This is mainly taken as the reference electrode potential. It means for all the metals or for all the electrodes which we take, this is taken as the reference. It means its value is taken as 0 and it is compared to all the different electrode potentials of the metals. From this electrode potentials, we have developed a electrochemical series, that is, the half cell potential values are standard and are represented as standard reduction potential values. So this is represented in electrochemical series. So remember this table of electrochemical series. See, you can observe here the value of hydrogen, it is taken as the reference one. It means it is taken as 0 and it is compared to the remaining metals. So according to this table, from bottom to the top, increasing strength of, you can observe increasing in the strength of reducing agent. From top to bottom, opposite to this, increasing strength of oxidizing agent, you can observe here. So this type, if these electrodes are used, oxidation or reduction can be defined from this electrochemical series. Next, cell potential or EMF of the cell. So this cell potential is known as the difference between the electrode potentials of two half cells. That is, E cell is equal to E cathode, E naught of cathode minus E naught of anode. It means cell potential at cathode minus cell potential of anode, which gives EMF of the cell. And this have, we can see a relationship between Gibbs free energy and EMF of the cell. EMF of the cell. See, whenever a work is done, it means whenever we will do a work, there will be no free energy left. It means if free energy is there, there will be no work done. If work is done, the free energy will be decreased. Decrease in the change in the free energy. See, when work is done is equal to decrease in the change in the free energy. Charge on 1 mole of electron, that is Avogadro number into electron charge. That means we need to multiply by Avogadro number and charge of the electron, 6.023 into 10 power 23 into 1.6 into 10 to the power of minus 19, which gives 96500. That is known as 1 Faraday. See, this is known as 1 Faraday by multiplying Avogadro number and charge of the electron, which gives the charge on electron mole, 1 mole of the electron, that is known as 1 Faraday. Here, how they are interlinked with the Gibbs free energy. you can see charge of n moles of electrons, charge is denoted by Q, that is n moles, number of moles is equal to, it is multiplied by the number of Faradays. See, Q is equal to N into F. The work done is equal to the charge into potential. The charge what we got here, N into F, and E cell, that is electrode cell potential, E cell. So whenever a work is done, you can see work is done, there will be decrease in the free energy. It means that free energy is denoted by the Gibbs free energy. Change in the Gibbs free energy, it is given by delta G. See, this is delta G. Why you can see a negative charge? Because there is a decrease in the free energy. That decrease in the free energy is represented by a negative charge. That is, this is the relation between Gibbs free energy and electrode potential, EMF of the cell. Delta G is equal to minus Fe cell. So whenever a reaction is spontaneous, then delta G will always be negative and EMF of the cell will be positive. When it is non-spontaneous, the delta G value will be positive and E value will be negative. When the reaction is in equilibrium, both values will be 0. Next we have the concept of Nernst equation. This is showing the relation between E cell and E naught of the cell. See, when the concentration is not equal to 1 molar, here E cell is applied when the concentration is equal to 1 molar. When it is not equal to 1 molar, we need to apply this Nernst equation. So when the concentration is not equal to 1 molar, then we use Nernst equation. So as per the thermodynamics, what is the delta G is equal to delta G naught plus RT ln of Q. See, what is delta G? Previously we have learned delta G is equal to minus NF E cell, and delta G naught, if it is not equal to 1 molar, delta G naught is equal to NF E naught. When we apply this in this relation, what we get? E cell is equal to E naught of cell minus 2.303 RT by NF log of Q. So this is the required Nernst equation. From this Nernst equation, we can see E naught is known as standard electrode potential, R is the gas constant, T is the temperature, and F is Faraday, and N is number of electrons gained or lost. So when we apply the value of N, when we apply the value of this Faraday, R at a room temperature, R and T values, will get the equation as E cell is equal to E naught of cell minus 0.0591 by N log of Q. What is this Q? This is the equilibrium. You can see this in chemical kinetics, equilibrium constant, that is concentration of the products by concentration of the reactants. Constant, reaction constant, that is represented here. This is known as the Nernst equation. So this equation is very much helpful for the problems. And next we can see here electrolytic conductance. Few definitions. Electrolytic conductance regarding this topic. We can see metallic conductors. So as we know, conductors means which allow electricity to pass through them. Here this metallic conductors, you can see the conductance in metals is due to the mobility of electrons. Yeah. Metals may conduct electricity in solid state, molten state, or even in dissolved state. When with rise in the temperature, magnitude of the metallic conductance decreases. With rise in the temperature, what happens? This magnitude of metallic conductance decreases. So this is all about metallic conductors. We have known it from the earlier, from the definition of conductors. And next we have another type of conductors, electrolytic conductors. So what is electrolytic conductors? Conductance is due to the movement of ions towards oppositely charged electrodes. We have seen in this both the cells, galvanic cell and electrolytic cell. It causes due to the transfer of matter and hence decomposition. One will be losing its electrons and one will gain its electrons. And next, electrolytes which are almost completely ionized. Which completely ionized, they are known as strong electrolytes. There are examples also here: NaCl, KCl, HCl, NaOH and ammonium nitrate. Next, electrolytes which do not ionize in a solution. Which do not ionize, those are known as weak electrolytes. Examples are here: CH3COOH, H2CO3, H3BO3, ZnCl2, HgCl2, HCN and H4OH. So these are about strong electrolytes and weak electrolytes. Next, to know in deep about the how a conductivity happens in electrolytes, we apply Ohm's law. So what is the Ohm's law? The current carried by a conductor is directly proportional to the potential difference between the two ends of the conductor. So here V is known as the potential difference, that is directly proportional to the current which is passed through it, that is denoted by I. So V is directly proportional to I, which is balanced by a constant, that is R, resistance. R is known as resistance here. V is equal to R into I. This is Ohm's law. So let us see what is resistance. Here, resistance of a conductor is directly proportional to its length and inversely proportional to its area of cross section. That is, if we take a wire in this way, when we pass electricity through this, the resistance R is directly proportional to the length. So this is directly proportional to the length and inversely proportional to the area of cross section. Here you can observe, if there is more area of cross section, there is less resistance. If there is less area of cross section, there will be more resistance. So that is what given here. The resistance is proportional to L by A, which is balanced by a equilibrium constant, that is known as specific resistance. This is known as specific resistance. So what is specific resistance? The resistance offered by a conductor of a unit length and unit cross sectional area is known as specific resistance. It means the resistance which we observe in a unit length, 1 unit of length and 1 unit of cross section, that is known as this specific resistance. Specific resistance is equal to R into A by L. If they are both are unity, this specific resistance is equal to the resistance. And next we can see conductance. So what is conductance? It can be denoted by C or by G also. It is the property of the conductor. It means which allows the conductor itself, allows the conductance, which facilitates the flow of electricity through it. It is equal to the reciprocal of resistance. So this is the unit of conductance, that is ohm inverse. This conductance is inversely proportional to the resistance. And next, specific conductance. This is denoted by the symbol kappa. So it is the reciprocal of specific resistance. So observe this, conductance is inversely proportional to resistance and this specific conductance is inversely proportional to specific resistance. This specific resistance is equal to 1 by this specific resistance. Specific conductance is inversely proportional to resistance, that is equal to L by R of A. So this is the definition of specific conductance. And next, what is meant by cell constant? So cell constant is the ratio between electrodes and area of electrode, length of the electrode and area of cross section. That is known as cell constant, represented by G star. You can see this cell constant is equal to L by A. Next, molar conductance. Molar conductance, this is denoted by lambda m. It is defined as the conductance of the ions produced by ionization of 1 molar of an electrolyte. Here we are taking 1 molar of electrolyte solution. The conductance developed in that 1 molar of electrolyte is known as molar conductance. The term specifies molar conductance. It means molar. We are taking 1 molar of electrolyte here. Here this molar conductance is equal to 1000 into specific conductance by molarity. And next, equivalent conductance. Equivalent conductance, that is lambda equivalent. It is defined as the conductance of all the ions produced by ionization of 1 normal solution of electrolyte. Here we are taking in molar conductance about molarity, and in equivalent conductance we are taking about normality. Here, which is the conductance developed by the conductance produced by the ions of 1 normal solution. So in place of molarity in the above formula we are taking normality, that is equivalent conductance is equal to 1000 into specific conductance by N. Next, one of the most important law, Kohlrausch law. This is very important topic. You can get questions from this topic, Kohlrausch law. Very easy topic of electrochemistry. So if you understand it clearly, you can answer the questions. What is Kohlrausch law? At infinite dilution, it means infinite dilution, we are decreasing the concentration of the solution and we are diluting it. That is known as at infinite dilution. What happens? An ionic species, that is either cation or anion, contributes, which gives a fixed value at a given temperature towards total conductance of the electrolyte, which gives a fixed value of conductance to the total conductance of the electrolyte. It means here we can see the ionic species conductance comparing to the total conductance of the electrolyte, that is irrespective of their ionic species in combination with it. See, you can see the definition here. Here we are taking at infinite dilution, a solution at infinite dilution. What happens? There may be X molar of its ions and Y molar of its ions. So that can be seen by applying this Kohlrausch law. If lambda naught of A and lambda naught of B be limiting molar conductivities of cation and anion respectively, then the conductances of the electrolyte is given by, so with their conductances is given in this way, that is on combining both this cation and anion we get a solution of lambda naught of A and B. Those we get by the combination of X molar of lambda naught of any of the solution with the ions A and B. Similarly, Y moles of lambda naught of solutions. This is the graph. This is the graph showing the relation between lambda m molar conductance and under root of the concentration. Here it is showing between CH3COH weak electrolyte and strong electrolyte between weak electrolyte and strong electrolyte. So if a weak electrolyte is taken, the graph between lambda m and root c is in a parabola shape. And what about to the strong electrolyte? It will be a straight line with decreasing straight line for strong electrolyte. For weak electrolyte it is a parabola, and for strong electrolyte it is a decreasing in straight line. Here we are taking it for infinite dilution. If we take a electrolyte at infinite dilution, this Kohlrausch law will be applied. Now let us see Faraday's laws. First law of Faraday's. What is first law of Faraday's? Here the amount of the substance deposited or liberated at cathode, the substance deposited at cathode, that is directly proportional to the quantity of the electricity passed through the electrolyte. So understand, whenever we pass certain amount of electricity through a solution, what happens? There will be oxidation and reduction reactions happens in that electrolyte, in the process. So whenever there will be some amount of substance deposited at cathode, that amount of substance is directly proportional to the amount of the electricity passed into that solution. Here it is given the amount of the substance deposited is directly proportional to the current passed into it, that is W is directly proportional to the I, the current passed into the time, that is given as, here I is the current in ampere which we are taking, and T is the temperature. For this, to remove this equilibrium, to remove this proportionality, we are adding equilibrium constant, that is Z. Z is a constant that is known as electrochemical equivalent. This Z is known as electrochemical equivalent, and this I into T is known as, denoted by Q, that is the charge produced when the current passed through it is 1 ampere and time taken is 1 second. See, when this is 1 and this is 1, what happens to the amount of the substance deposited? That is equal to Z. That is, the amount of the substance is equal to the electrochemical equivalent. Now, second law of thermodynamics. So, what is second law of thermodynamics? When the same quantity of electricity is passed through different electrolytes. Understand? When same quantity of electricity is passed through different electrolytes, what happens? The amount of the substance deposited or liberated at the electrodes, amount of the substance, obviously either reduction or oxidation happens, and the substance deposited or liberated at the electrodes, that are directly proportional to their equivalent weights. Equivalent weights are involved in the second law. So the same amount of electricity is passed through the different electrolytes, and the substance which is deposited or liberated at the electrolytes, that is directly proportional to their equivalent weights. You can see by this formula we are passing the electricity to two different types of solutions, A and B. What happens? Some amount of mass of A and B will be deposited, that is mass of A by mass of B. We are taking ratio of mass of A and mass of B, that is equivalent equal to the equivalent weight of A and equivalent weight of B. So these masses are denoted by W1 and W2. Those are equal by E1 by E2. Equivalent weights. This equivalent weights, the weight collected here, this from the first law, what is the weight collected? That is given by Z into Q, that is the electrochemical equivalent into the charge. That is, for first solution we are taking as Z1 and second solution we are taking as Z2, and same amount of current is passed, right? That is, Q is kept same, that is Z1 by Q by Z1 of Q by Z2 of Q is equal to E1 by E2. It means the electrochemical equivalent is directly proportional to the equivalent weight. See, Z is directly proportional to E. So this is known as the second law of Faraday. And next concept we have about batteries. So as you can observe the type of batteries in your home also. We have two types of batteries. Let us see what are batteries. Those are the source of electrical energy which may have one or more cells connected in series. One or more cells, we can connect them in series. For a good quality battery, it should be reasonably light. It means it should be less weight, it should have good compact, and it should have its high voltage, which should not appreciably during its use. There are two types of batteries. They are primary batteries and secondary batteries. These two types of batteries which we can see in our home also. These primary batteries, for example, the batteries which use in the remote, in watches, those type of batteries, those are known as primary batteries. So in this primary batteries, the reaction occurs only once, and after use over a period of time, this battery becomes dead. This cannot be reused. So this type of batteries are known as primary batteries. For example, if we are taking a dry cell or Leclanche cell, what happens here? The anode is the zinc container. You can observe in this pic. This is the type of batteries which you use in your home. The anode here is the zinc container, the outer wall of this cell, that is zinc container, and the cathode we use here is the graphite rod surrounded by MnO2 powder. This cathode, this is the cathode, this is graphite. Graphite which is surrounded by MnO2 powder. Here the electrolyte is the paste of NH4Cl and ZnCl2. This is the electrolyte. What happens when we introduce this battery into a device? What happens? There will be cathode and anode reactions. What happens at cathode? This MnO2 reacts with this NH4 plus ions. By gaining 2 electrons, it is converted into Mn2O3 and ammonia gas by releasing water. This type of reaction you can observe at cathode, and at anode what happens is this zinc is converting into Zn plus 2 by releasing its 2 electrons. So this type of reactions happens in dry cell. With this type of reactions, the electrons here released will produce energy, will produce electricity, which helps in working of the device. And next type of batteries is secondary batteries. You can see this type of batteries in inverters. Yeah, these are very light, and these secondary batteries are very huge to lift also. You can see these type of batteries in the inverters, and these can be recharged. So the above batteries, primary batteries, are not recharged, but these can be rechargeable batteries. And you can see what is for example, this one of the example is lead storage battery. What happens here? The anode here is spongy lead. The spongy lead here, you can see here, the anode here is the spongy lead, and cathode here is the grid of lead packed with PbO2. See, you can see here, this is the cathode and the above is the anode. The sponge one is the anode, and this PbO2 is known as cathode. The spongy lead here in the arrow mark, This is anode and the PbO2 layer is known as the cathode. The electrolyte is 38% of H2SO4 solution. So here you can see in between this cathode and anode we are having the electrolyte, that is 38% of H2SO4. What happens, the reaction here at anode, what happens is the lead reacts with this sulfate ions and it is converting into PbSO4 by releasing 2 electrons. And at cathode what happens, since this is in its oxide form, lead oxide, this reacts with the sulfate ions in the electrolyte and with the H plus ions in it. Since it is an acid, it releases its H plus ions and it releases 2 of its electrons. It is finally converting into lead sulfate, releasing water. So the net reaction of this cell will be this lead solid reacts with this lead oxide in presence of H plus H2SO4, that is it is releasing its H plus and sulfate ions. Excuse me. It is converting into its sulfate form, lead sulfate and water. When this is recharged, this PbSO4 is again converting it into its ions. Excuse me. This PbSO4 is again converting it into ions and it is again used for generating energy. See, when recharged, all the cell reactions will be reversed. This will be reversed and it will again converting into its lead oxide and PbO2 and Pb form. And next we have fuel cells. In fuel cells, here we are using fuels like hydrogen, methane and methanol. They are used as the source to produce electrical energy, so they are known as fuel cells. These are pollution free and have high efficiency. So these are pollution free and they give lot of energy. One of the example is hydrogen oxygen fuel cell. So what happens here? The electrodes which are made up of porous graphite. Porous graphite means there will be holes, small minute holes present in the graphite which are impregnated with catalyst. They have a catalyst like platinum, silver or a metal oxide. You can see this is the fuel cell. What happens? Here the electrolyte is the aqueous solution of KOH or NaOH. Here the electrolyte, we are taking it here as KOH or NaOH. And next, oxygen and hydrogen are continuously fed into the cell. It means there is continuous passage of oxygen and continuous passage of hydrogen. You can see in this pic, they are both continuously pumped into this cell. What happens? Oxidation half cell reaction. Hydrogen gas which we are inputting it, that reacts with OH minus which are present in the electrolyte. They convert into water, releasing electrons. This is happening at anode. At cathode, what happens is the oxygen gas which you are inputting, it reacts with the water molecules by taking 4 electrons and it is converting into OH minus ions. The net reaction happening is hydrogen reacts with oxygen converting into the water molecule. Since there is no other type of metals which are harming to the nature, this is pollution free and it gives high efficiency. The EMF of this type of cell is 1 electron volt, and here the thermodynamic efficiency, that is denoted by neta, that is equal to delta G by delta H. As we know, delta G is equal to minus NFE and this is delta H. You can see the hydrogen gas is continuously inputting here and the oxygen gas is also continuously inputting here. Here it undergoes oxidation and reduction reactions and water is eliminated out. This produces energy which is environment friendly. And next we can see the topic of corrosion. So what is corrosion? The process of slowly eating away the metal due to attack of atmospheric gases. The gases present in the atmosphere will eat away. It means they will react with the metals and they will get the impurity of the metal will be formed, that is on the surface of the metal, resulting in the formation of oxides, sulfides and carbonates. It means the atmospheric gases react with the metals and converts it into its oxides, sulfides and carbonates. This is known as corrosion. We can observe corrosion of iron. General example, it is forming a rusting. So the rusting of iron, it is denoted by Fe2O3 H2O. It reacts with the water present in the atmosphere, oxygen present in the atmosphere, converting it into its oxide. So the factors which promote corrosion is the reactivity of the metal. When it is highly reactive, it reacts readily with the atmospheric gases, and presence of impurity. If there is impurity in it, that also results in corrosion. And when it is exposed to air and moisture, it also corrodes the metal. And strains in metal, if there are strains in metals also, it will be corroded. And presence of electrolyte, if electrolyte is present, there will be it can undergo oxidation or reduction reactions and it will be corroded. So what are the steps taken to prevent corrosion? So in order to prevent corrosion, we are taking few steps, that is barrier protection. By using paints or thin film or oil or grease, by applying all these types, we can prevent the corrosion. If we paint this type of things on the metal, it will not be corroded. If there is any breaking in this protection, the metal which will be get corroded. If we take iron, it will get rusted. Next, sacrificial protection. What is sacrificial protection? Covering the surface of iron with a layer of metal which is more active than iron. Which is more active than iron, which means the metal which is more reactive than iron. If we protected iron with that metal will react first with the atmospheric gases. So that is sacrificial protection. And next, galvanization. This is also the same, covering iron with metal zinc. That process is known as galvanization. It means a layer of zinc will be surrounded by the zinc iron metal, which prevents it in contact with moisture, oxygen or carbon dioxide present in the air, and form protective invisible thin layer of basic zinc carbonate and Zn zinc hydroxide. This is formed around the iron. This is due to the galvanized iron sheets lose their luster and turns it from protecting it from further corrosion. Since this zinc carbonate and zinc hydroxide is galvanized around the iron, it will be further protected from corrosion. And next, electrical protection or cathodic protection. That is, some more electropositive metals like zinc, magnesium or aluminum, they may be connected with the iron pipes buried in the moist soil, underground soil or canals or storage tanks, which will protect iron from corrosion. Here iron will act as cathode and it will not get rusted. That is electrical protection. Next, use of anti-rust solutions. That is, these are alkaline phosphate and alkaline chromate solutions. These are alkaline in nature and solutions prevent the availability of H plus ions. This does not produce H plus ions. On the surface of the iron, a protective insoluble thin film of iron sulfate is formed which protects it from corrosion. So these are the steps to prevent corrosion of the metals. So this is all about electrochemistry. I hope you all understand this topic, and thank you for listening.